good. Thank you, Bart. So my name's Klaas. Let's keep it simple. And I want to talk about functional programming, specifically functional programming in Swift. I guess this is a little bit about my functional journey because I made a lot of mistakes along the way, and I'd like for everyone who hasn't started yet to not make my mistakes. I actually tried to pick it up several times. I started with JavaScript and somewhat functional. You can do cool stuff with it. It has no strong types, so you can also break a lot of stuff. But I think the main thing that I failed on when I started doing functional programming was I approached it as if I was learning any other imperative language. So when you know Swift or Objective-C, learning Ruby or Python or JavaScript or any other imperative language is mostly learning new syntax, lots of new APIs, but you know how a subclass works, you know how a class works. They all have some sort of prototype or interface or something that you can do to sort of make those things. So you don't really have to think differently. Whereas with functional programming, it's a completely different way of thinking. You have to kind of start from scratch. I've been told it's easier for people who have no prior experience in programming at all to pick it up than for lots of us who probably do have experience to relearn this new way of thinking. So hopefully by the end of this talk, you won't make my mistake and realize that functional programming is a completely different way of thinking about things. And you can't just be like, I know Swift, I know Ruby, let's do Haskell. All right, so what's functional programming? This is kind of the obligatory slide of Wikipedia quote. Wikipedia says it's a programming paradigm that treats computation as the evaluation of mathematical functions and avoids state and mutable data. It's a lot of words. I think what I find most important, or at least the most important thing in this sentence, is avoid. Our programs live in the real world, so as much as we want to avoid having state and data, in the end, we will have a user. A user can or cannot be authenticated. That's state. And he or she might have a phone number that can change. That's data and also state that changes. So at some point, even in the functional world, you're going to have to go play in the real world and actually change things. But you want to prevent that for as long as possible. So quick aside on naming. When you start functional programming, you see a lot of things like this, where it's a T and an X and a T and a T. I'm going to do that too. And yes, it annoyed the hell out of me too when I started. But at some point, you realize that it's not the names that matter. It's the type of things that matter. In Haskell, there's ways to implement this without even having a variable name somewhere in the middle. Swift kind of can do that if you use closures, but they're limited in other ways. So we're stuck with a function. You can't have a generic closure. You can do let ID and then have a generic type because Swift. So we're stuck with this. I could have done this, which is saying exactly the same thing. We have anything, literally anything. It can be everything, any possible type in Swift that you can imagine. We have a variable, and that's also an anything, and it returns an anything. I don't think the names matter because if you look at the types, this is the identity function. It's a special type of function that returns what you give it. If you give it a 1, it returns a 1. If you give it an array, it returns the exact same array. If you look at the types, it can't do anything else because it doesn't know what T is. T could be an array. If it knows it was an array, it could append to that array, or it could add another array to it. But you don't know when you're inside this function. It's just a T or just an anything. So like I said, the names don't matter here. It's about the type T or the type anything. And in this function signature, you can't do anything with it except return it. So that's what it does. Apple kind of agrees, I guess, because if you look at their implementation of optional, they have like this wrapped generic type, which is kind of what it is. But then when you look at the function signature of their map implementation, this came straight from the Swift repo on GitHub, there's this U all of a sudden because that's also a wrapped. So what are you going to call it? the definition of map is that you can change the type of what's in there. So if you call that wrapped as well, all of a sudden, all you can do is return an int from an int. You can't say, I have a string that I think contains an int, so I'm going to return an int if it's there, or a none if it's not there, if both of them were wrapped. So Apple kind of breaks down on their naming. I'm going to use T and U pretty much consistently, and F for functions. Mostly because later on I want to show some similarities between different functions, and it's a lot easier to line them up if everything is kind of named the same. I also stripped out all of the add escaping and throws and all of those things because you do need them in Swift, but they kind of get in the way of the points that I'm trying to make. If you take these things from my slide, the compiler will warn you. There's also great GitHub repos that have already implemented most of probably everything of what I'm going to show, so probably better idea to copy that anyway. So the first step on my functional journey, it was JavaScript. And it's years ago. It was around the time when they were trying to figure out how to run callback HAL. We had all these asynchronous stuff. We had AJAX requests, and that resulted in something called callback HAL, and they solved it with something called promises. This is callback HAL. It's some fictional API. It's a really bad API. Which tries to get a name asynchronously, and then tries to get an H also asynchronously, and only if both of those things exist can you create a person out of it. And then we have to handle the error in case there isn't an H, and then we have to handle the error in case there isn't a name. So we have two places where we handle the error, while we're probably going to handle them exactly the same way. So this is going to lead to duplicate code or a duplicate function call to the same function, which at some point you're going to forget to add to an else, and then you have a bug. And this complexity will grow with every property that you add. The nesting goes deeper and deeper until you give up and you go insane. The JavaScript community, adopted promises. This is not an idea that they thought of themselves. It's something that exists before JavaScript. This is the same API, but implemented as promises. So you get the name, which is a promise. You get an H, which is a promise. And if both of them are fulfilled, then you can construct a person from that name and that H. If either one of them fill or both of them fill, you get an error, and you only have to handle it once. At the end, JavaScript isn't typed, but if it was, you would get a promise generalized for person back, which could either be pending, there is no person yet, or fulfilled, you have a person, or now I have to remember my naming. I think it's rejected, in which case there will be an error. This is the magic method, and there's a couple of implementations in JavaScript. Like I said, JavaScript is untyped, but if there were types, then this would kind of be the type. There's two variants of this method, actually three, but for our purposes there are two. This is the variant where, given a function, you return a new promise, which the outerlying promise that you call then on will then adopt. If that promise is pending, the outerlying promise is pending. If the new promise is rejected or fulfilled, the outerlying promise will become fulfilled. Also, when a minute later it changes from pending to fulfilled or rejected, the outerlying promise will copy that. The second variant is kind of the same, except you have a type and you return another type. It's not a promise, but it's then lifted into a promise. And the same thing happens here. That promise that is returned is then adopted by the outerlying promise, and the state remains synced in a way. So after JavaScript, I did Objective-C for a while. Wasn't much functional going on there. Then Apple announced Swift, which gave us these new strong types called optional and array. And there were all sorts of third-party libraries that added some more types. I didn't know back then, but all of these types have something in common. You can kind of see it from their type signatures because they're all generic over one, or in the case of result, two values. But they have more than that in common. But first, my functional journey went to Argo. Kind of funny. I never talk about Argo, and we were having dinner, and someone else brought it up tonight. It wasn't me. At least I don't think it was me. Nope. I started using Argo. One of my first Swift projects, I introduced Argo mostly because I liked it. It was a great way of JSON parsing. It took care of error handling. This is kind of their, I guess, typical example. You have a parent that has a name and age and children. And then JSON is just a dictionary, but it's mostly used for JSON parsing. You take out a name, you take out an age, you take out a children. In the end, you make sure that a parent actually has children, because otherwise it's not a parent. At the time, I had no clue what this was doing. Does anybody else know what this is doing? Like under the hood? Kind of. Right, so at the time, it was pretty much the same for me. I copied whatever was in the README. I was in an iOS developer Slack with the Thoughtbot folks who built this, so if I had a question, I asked them, and they were always very nice, and they answered me. But it was mostly just copying and pasting, like when I started with PHP way back in the day. Then I actually joined Thoughtbot, and they have this thing called Investments Days, where you can spend a day of the week investing in yourself. So I decided to learn Haskell, because I knew this was inspired by Haskell. So I spent some time on that. That's the path I took. We're going to kind of skip over to Haskell here, because we're talking about Swift. So I'll do most of the examples in Swift. There will be some Haskell, but not mostly just type signatures. So let's go back to map, and let's look at the type signatures of map. And they already kind of look similar, but remember that the question mark and the array are syntactic sugar. So what happens if you remove the syntactic sugar? They're almost exactly the same. The only outlier is result, again, because it has two generic types. The thing to remember about that one is that map transformed the leftmost generic type. So in the case of result, it transformed the T, and it leaves the error alone. Whatever error is in there is going to stay the same. For all the other ones, it's just going to change the T into a U, which could be the same type, could be a completely different type. There's actually a name for this. This thing is called a functor. And all of these types that I shared all share this thing. They're all functors. This is a hypothetical implementation. Swift doesn't support higher kind of types, and to make this protocol work, you need higher kind of types. So we're stuck with having to re-implement the type signature for map for every functor that we can think of. And these things have laws. And this is the most fun part, because these things are incredibly hard, and I'm not going to do them justice because they're mostly just weird functional syntax. I think the important thing for now is to know that these laws exist and that they are important because they tell you what a functor is, and if a functor doesn't abide by the law, then you will have bugs because you think it works in some way and it doesn't, and well, someone is going to get angry at you. I think the only way to really understand these laws is to implement your own functors and test your assumptions, test that these laws work. You will probably make mistakes. There's ways of testing that will tell you that you just made a mistake, and then you can figure out what it is. It's mostly trial and error and gaining like an intuitive sense of what these things mean. So I'll go over them quickly. But if you really want to know what these are, then you should probably just practice with a bunch of your own functors. I'll define these in Haskell because it's a lot more succinct. I'll try to give Swift examples like I did here, but I don't think I always did. So the important thing here is that fmap in Haskell is the global version of map in Swift. So where we call map on a type, in Haskell you call fmap, and then you give it the type and the function. But basically this is saying that mapping over an ID is the same as applying the identity function directly to a functor. And this one's going to be a little bit harder. This is composition. In Haskell, the dot is function composition. So it basically means that the return value of f is the input value of g, and that becomes a new function. I've defined it here as, what did I call it? The arrow operator, or the forward compose operator, because Swift doesn't let us use the dot, probably for good reason, because it would get really confusing in Swift if you use the dot for this. And this is basically saying that mapping a compose function should be the same as composing the mapping of the two functions. Again, you should probably just try these out for yourself, try to test some of these. They both are about structure preservation. If you have a functor, then map should return that same functor. If you have an array, then after you're done mapping, you will get an equal length array. The element inside the array can change, but the array itself cannot. The same for optional. You can change whatever is inside the optional, but it has to remain an optional. You can't return a result or something else from a map. The way to test these things is traditionally we test things. We put one or two values in, and then we make sure that one fails, one succeeds. It's kind of hard for these laws, so most functional languages, and Swift also has implementation for something called quick check, which you define these laws programmatically, and then quick check will try hundreds or thousands of different examples to try and break your implementation. It will tell you which example it used to break your functor in this case. These are just three. Chris Idop wrote a post. It's not an actual library, it's just like he wrote out how to implement one yourself. Then there's a bunch of GitHub repos. When I Googled it, there were a bunch more, so there's plenty of choice. Before we move on to the next type class, because there's more, we have to talk about currying a little bit. We already talked about currying too, it's fun. But it basically means that you take a function that takes multiple arguments and return a sequence of functions that all take a single argument. Haskell does it by default for you. Swift removed it in Swift 2, I think, so you have to do it yourself. But basically, we have a person. You can initialize it with a name and an age. Normally, you give it a string and an age, and the int directly. But if you curry the function, then you get a new function that takes a string, which returns a function that takes an int and returns a function and returns a person. So if you want to call that, you do curry person init. Then you call the first function with a string and the second function with an integer. And in the end, you end up with the person. Now let's have some fun. Let's say name and age are both optional, and you want to construct a person. The default way in Swift, I guess, would be to use if let. And I'm aware that this could be one nested if, but I'm going to make a point later. Actually, I'm going to do it now. Look how similar this is to what we did with promise earlier. These things are kind of the same. The level of nesting is the same. The error handling is the same. If we add another property, the level of nesting is going to be the same again. The error handling is going to be the same again. So let's try to solve this with a functor. We still have an optional name and an optional age. And we map the optional name into the curried person initializer, which gives us back a function from an int to a person that is optional. The function is optional. And it becomes a problem because we can't just map the age over an optional function, because when you map it, inside that map, you get an optional function from int to person, and you're trying to give it an optional int. That's not going to work. We could do this, which is you map over the x, which in this case is that optional function from int to person. I need to get my type straight. Then you get an f, that's an int to a person. You map age into that f, and in the end you get an optional person. And then you return that again, and it becomes a double optional person, which is not fun. And this is the best way we can get by just using functors. It becomes even more fun if you add another property, because you get a triple optional. yeah, I don't really want to deal with triple optional, so let's see how we can solve it. There is a type class called applicative, which has the function apply, which would look like this if you used it. And in the end, you get a single person back. What you're kind of doing is you're applying the result of another result into that optional function. This is what it would look like for optional, and unlike map and flat map, which are implemented by default, apply is not implemented in Swift, so we have to do it for every type ourselves. This is just a possible implementation. Later on, we're going to refactor it, and we're going to make it a lot better. But essentially what it does is it makes sure that there is an x, that there is an f, and then it applies the f to the x, and if either one of them is none, then it returns none. Slight aside, I prefer using the enum values of optional instead of nil. Just a preference because it's an enum, and nil is just syntactic sugar. But wherever you see none, you can see nil. It kind of works the same. And applicative is very similar to map, except instead of just a transformation function, it takes a applicative that contains the transformation function, and then returns an applicative with the new value. This is a little better than what we had, but it's also kind of weird because our person takes a name, an age, and children. But if you read this from left to right, it takes a children's array, an age, and a name. And that's where all those funky operators come in. So both of these have their own operator. The first one, map. I forgot the names, but they also have names that you can speak in English. But for now, we'll call it map. It has the exact same type signature. The same goes for the apply operator, which is the one with the asterisk in between. And their implementations are really simple because you just call through to whatever we already implemented on optional in this case. Swift does not have higher kind of types. In a language with higher kind of types, this is the stuff that could be done automatically because you know that something has a map if it is a functor, so you can also automatically define that it has an operator. Swift doesn't have these at all, so it's up to us to define them for optional and array and any of the other third-party type that we decide to include. And with these operators, we can make it like this. We query the person initializer, then we map the name into it, then we apply the age, and then we apply the children. And you can see the function signatures, the type signatures that this uses on the right in comments. In the end, you either get a person, so a .sum person, or if any of these is none, then it will short circuit and you'll get a none. So this is kind of the same as Argo. And unlike me, when I started using Argo, we should be able to read what's going on here and realize that this is a functor and an applicative. Before we can move on to the applicative laws, there is one tiny piece that we need to include as well. An applicative also has a function called pure, which all it does, it lifts a value into an applicative context, into an applicative structure, I should say. I've declared pure as a global function. It's a preference. Some declare both as a global and as a static function on the type. Some declare it global, some declare the static. It's up to you. You can do both. Probably the best way if you want to support other developers. For now, it's a global. And let's see how this can be useful. Let's say we need to do result because Swift automatically lifts optionals when necessary, so we can't use optionals anymore. But let's say we use results instead, and the name and the age are both already results, but children is defined in the app, doesn't come from an API, so it's not a result. It's just the children's array. If you now try to use this same flow, then you get an error because it's expecting a result that contains an array of persons, but we're giving it just an array of persons. Like I said, Swift would automatically solve this for us because as soon as it sees something that's not optional, it will just lift it to an optional for you. It can't do that for third-party types, unfortunately. So we use pure and all it does is say pure becomes pure lifts that children array into our applicative context. I was going to say something else, but it slipped my mind. Anyway, the loss. This is fun. The identity and composition laws are mostly the same. They preserve structure. All of these laws are kind of about preserving structure and making sure that none of these operators actually change anything about the applicative or the functor itself, just the inside, what it contains. Homomorphism essentially says that the effect of applying a function that is embedded in a structure to a value that is embedded in a structure should be the same as applying a function to a value and then embedding that result into that structure. And then the interchange law states that it doesn't matter if you choose to lift a function into the left or right side of apply. And again, it's important to know that these exist, but I don't understand these half the time. It's better to just write the test, make sure that whatever you write conforms to it, and then if you ever break it, the test suite will tell you.
What does the dollar mean in this context?
How am I going to explain it? It's also function application, but it has a lower priority. So you can use it at the end, and then you don't have to use brackets. And in this case, it's used as a partial function application, I guess. So yes, it's important to know that these exist, but I'm not going to be able to give you an intuitive sense of what these do by just talking. You have to try it out, play with them, write some tests, break them, see why they're broken, and what kind of problems you can cause, I guess. So let's move on. Let's move a step further. Let's say we have a parent class. It's also kind of a person. I didn't bother to make a protocol out of it or anything, but it's kind of the same thing, except that now it needs to have children, because a parent is not a parent if he doesn't have children. So our first attempt could be to use map and apply, and then validate and map that over to parent, and we get a double optional back. The same if we use apply. We again get a double optional back. This is because when we call validate, parent is an optional functor and applicative, and they cannot change the structure of the return value. So when validate returns an optional that is embedded into the structure that was already there, which is also an optional, and you get a double optional back. And now we get to the magic one. That's where monad comes in, because it is allowed to change that structure. And unlike applicative, Swift does provide default implementations for this one on both optional and array. And this is what it looks like. It looks if there's an x, and then applies the function to that x, or returns none if there is none. There's also an operator called the bind operator, which again will just call back into what Swift has already defined for us. And monad essentially removes a layer of structure. So if we use the monad, then all of a sudden we can do this. We can call validate at the end, and that will return either a parent, or if it has no children, none. And again, this will short circuit, and the parent that it returns will be none or some if it has children. Again, monad also kind of aligns with applicative and functors, because they're all trying to do the same thing, but on higher and higher levels, I guess you could say. Note that I did use I should look it up, right associative operator for this one, because that one aligns a little bit better, but it's essentially the same, except the arguments are reversed. Monads have loss too. Note that return is monad's form of pure. It is exactly the same thing as pure. It lifts the type into a monadic structure, but I've not seen it used in Swift, probably for obvious reasons. Pure is exactly the same, and return is very confusing. The right identity law states that lifting a structure into itself is the same as the structure itself, so it shouldn't add another layer of structure, it should just return that structure. The left identity law states that flat mapping a function returning a monad or a structure over a value is the same as calling that function with that value. And then we have associativity, and it again states that the order in functions are in which functions are applied does not matter as long as the sequence of operands is not changed. All right. Let's talk about Swift's monad laws, or how Swift is not always monadic. Swift's optional.flat map is. Swift's sequence is not, and that's because sequence is a protocol. And the law states that if you give it an array, it should return an array, but because sequence is a protocol, you can technically flat map something over an array and return a set from it, which violates these laws. I don't think it's a big problem, but it's definitely something that more functionally pure people will get upset about, probably. And then there's also the famous one. There was just a lot of bike shedding on the Swift evolution list, or I guess it's a forum now. This is the one that when you give an array of optionals, it will return an array without optionals, which is not monadic because it changes the length of the array. It will actually remove elements from it. In Swift 4.1, it will be renamed to compact map because it was confusing and combined with the lifting of optionals, it could actually do really, really weird things. I suggest you read the proposal of why this should be changed. They had a couple of examples where you could get really weird behavior if you didn't realize that this was filtering out nils and Apple was automatically lifting nils. But anyway, it's going to be removed in Swift 4.1, so you should be fine. So let's do some refactoring. This was our initial implementation of apply. But we can use monad. And now it's this. And the cool thing about this one is that it mostly applies to every applicative if it has a monad. You can implement it in this way, and it kind of works for all of them. I should also say that a monad is always an applicative, and an applicative is always a functor. Did I say that the right order? So let's get back to Argo. And this was our example, and now we should be able to figure out what's going on here. So what's going on here is that we query the parent initializer, then we map, and we get this JSON with a weird other operator and a name, but all we really need to know here that this is a custom operator that pulls out the string name from a dictionary. I saw that they want to rename this because there is precedence in functional languages for this operator that is not doing this. So they kind of want to rename this operator, but it's still there, so let's use it. This actually is a decoded. So I think it's actually pretty magical that we've been using optionals all this time, but now JSON with the operator and name returns a decoded, which is a completely different type, but it looks exactly the same. Even the function implementation is mostly the same, except now we have to return the decoded success or a decoded failure. But everything else is kind of the same. So let's look back at promise. Remember these two methods? They look kind of familiar, don't they? They're actually just flat map, and promise is a functor and a monad and an applicative as well, which means that we can do the exact same thing with a promise. Except now, except for the validate function, pretty much all our code all of a sudden is asynchronous with exactly the same chain of operations. And at this point, we have a pending promise, which, because the children array is still pending, we didn't give it a value. So if we give it a valid value, then this will print a parent. If we give it an invalid value, no children, this will print an error. It's also a nicely typed error. If you go look for promises library online, you will probably find Sarush's ones, which uses Swift's error handling. There's good reasons for it, but they're untyped, so it's kind of like you still have to handle all the possible errors in the world instead of just this one. But I based my implementation off of his, so it's a pretty good library. So by abstracting our code into higher kind of types, we were able to define our computation as the evaluation of functions. And because of these higher kind of types, we don't even really have to care about what structure is underneath. We don't really need to know if it's an optional or a decoded or a result or any of the other possible type classes there are. In our examples, we used synchronous, optional, Argo's decoded, and result. And we used this almost the same code to make it asynchronous using promises. So let's recap. It's a programming paradigm that treats computation as evaluation of mathematical functions and avoids state immutable data. At no point in that function chain is anything mutated. There's no state really, except maybe how far you've applied the queried function. I think the point kind of is to stay in that functional land for as long as possible and only try to reach into that structure to reach the value or the error when you need to do something with it. And that's why all these operators are useful, because they allow you to stay in that functional land without having to if-let or switch over these things. They allow you to avoid if-letting and switching until the last possible moment when you actually have to perform something with the value. In our example, that would probably be presenting either the user, the parent or the person to our user, or show them an error that maybe they don't have enough children. So this could be a valid person object that you display in a view, or it could be like a UA alert or an NS alert that you show with the error of what actually happened. This is just a very brief overview of functional programming, because there's much more type classes. There's semigroups, there's monoids, there's readers, there's writers, there's state, there's alternative, and tons more. They all have their own laws, they all have their own uses, they all have their own applications. But yeah, there's a limited amount of time. I have some books that I can recommend, so hit me up after. Questions for right now?
Actually, I wanted to ask maybe post the slide somewhere. I found this incredibly helpful.
Which one?
I'd like to go again through the whole thing.
you want me to start from scratch?
No, my own,
Which one?
No.
If you will post a slide somewhere.
Yeah, oh yeah, I will post them somewhere. Yeah, I will post them somewhere.
Okay.
Yeah, sorry, I didn't understand the question. I will post a slide somewhere. They're Dex that did it, so they're all marked down and searchable. What's up?
I was wondering, what's the reason why those Wix symbols are chosen? Why not just
Haskell.
Haskell?
They are kind of the same as in Haskell, except Haskell, so I don't remember which one. So the star in Haskell is actually a $sign, but Swift doesn't allow you to use a $sign in your function signatures. The same for bind. The minus sign in the monadic bind in Haskell is an equal sign, but Swift doesn't allow you to use that in your custom operator. So they're very similar to Haskell, but changed mostly because Swift doesn't allow you to use them. I don't know if there's precedence in Haskell or if there's someone who's just like, I like star. Let's use star or $sign, I guess. No more questions?
Do you use this in your day-to-day work?
Not in my work, because I have a coworker who literally told. I linked him the runes repo, and it says something like inscrutable symbols that some people claim have meaning. I linked him there, and he replied back, inscrutable peoples that don't have meaning to me, or something like that. So no, not in my day-to-day work, but I do have some open source stuff that it was. I wanted to do screen recording, which is very hard because there's lots of optionals and weird things. So I applied like a functional layer on top of it. It's an open source repo. It's called Letters, in case you want to. So it's my first name / letters on GitHub, and you can find it. There's some functional stuff in there. I would like to use it more, but I have to deal with other developers who have preferences. And it would probably make onboarding new developers a little harder because you have to teach them all of this from scratch.
Well, it's just an hour or so.
Yeah, but then there's a lot more. There's a repo, Point Free Co, I think. They just started a screencast where they kind of do this, but then all the way from scratch. These are actual, at least one of them I think is an actual mathematician, so he actually knows like where this all is based on. Super smart, and they do show like some ways to make this applicable to your everyday code. Also in such a way that it doesn't mess up like everything. Like you can keep it nice and contained in a library somewhere, maybe a style library, and then the consumer of the code doesn't even have to care that somewhere in there is a semi-group. So it's possible, but you have to keep it contained, I guess. Anything else?
I was wondering, the monad thing, is it the same as reduce or fold in other languages?
So folds are a little bit different. A fold is basically a generalization of some of these concepts. So you can have a fold A, which, let's see if I can find an example. So the first 3 lines, the map and the apply and apply, this happens so often that there's a function called lift A3, I think, which just does this for you without having to use the operators. And I think that's the max that you can use. So yeah, there are functions called lift that do this for you without the operators. But as soon as you add more than 3, I think you have to do it like this. And there's also one called lift M3 that does this for monads.
Yeah, you mentioned a couple of higher types.
Yes.
You also mentioned that the function programming you don't have state, but one of the types was state.
So you do have state. You just try to push it to the edges of your program as much as possible. So you try to keep in this functional land for as long as possible, and only when you really need to do state, then you call out to a database, change the state, and then go back to this functional world as quickly as possible and keep on. It's kind of a perfect world because nothing can be mutated, nothing can be.
What you mentioned, there was a higher type called.
Oh, there's a higher type called state. Well, that's where my knowledge is lacking because I also just started in stuff and I know it exists. I know kind of what it does, but I couldn't explain it right here.
Okay.
I'm sorry.
No problem.
Oh, thank you, Klaas.
Thank you.